the Neuenhaus tensor. Nj of an almost complex structure. It satisfies. Right, so for any vector fields v and w on X, we will have Nj of v comma w. So this is going to be an equation in vector fields. So Nj is NABC, and Nj of v comma w is NABC VBWC, meaning that you take the vector fields and you contract them with the two downstairs indices in n. This is going to be equal to the Lie bracket of v and w plus j times big brackets the Lie brackets of jv against w plus the Lie bracket of v against jw, close big brackets, minus Lie bracket of jv against jw. And this is true for all vector fields v and w in the smooth sections of Tx. So this looks quite like the definition I gave of the curvature, or the kind of characterizing property I gave of the curvature and of the torsion of connections. So it's a fact that the right-hand side involves derivatives of v and w. So each Lie bracket involves either one derivative of v or one derivative of w, and so on. But all the derivatives of v and w on the right-hand side cancel out. So the left-hand side is pointwise linear in v and w. It doesn't involve any derivatives in v and w, and so that's a kind of a property of this complicated expression here. A bit like the curvature being depending only on the zeroth derivatives and not the first and second derivatives of the property of the defining expression. Okay, so you can think of Nj as like a kind of curvature, except what is better, in fact, to think of it as the torsion of J. In fact, it is literally the torsion of J in the sense of G structures, GLMC structures. Okay, so there's a big theorem about Nj called the Nylander-Nirenberg theorem, which says that if we let X and J be an almost complex manifold, so then a necessary and sufficient condition for there to exist local complex coordinates so I'm going to take X, fit inside it, I'm going to take a small open set U, let's say a small ball, then I'm going to take a map from U into Z1 up to Zm, can be a map from U into C to the M, which are kind of local diffeomorphism. So a diffeomorphism from a small open set in X to a small open set in C to the M, and these should consisting of holomorphic functions so each of these from U and J into C. So I gave you a definition of a holomorphic function on an almost complex manifold. That's what I mean here. Okay, so necessary and sufficient condition for there to exist local holomorphic coordinates. Well, this is on all of X, meaning that you can cover X by open sets U for which this holds. So necessary and sufficient condition is that the Neuenhaus tensor Nj is 0. Okay, so if the Neuenhaus tensor is 0, we can find such local holomorphic coordinate patches. If it's not, then we can't. So this is like a kind of curvature equals 0 condition. It's rather like asking for something to be flat. And okay, there's two directions here. One of the directions is actually quite easy. If you assume there exist local holomorphic coordinates, then you can kind of play with this thing and prove that Nj has to be 0. And for example, if there are local coordinates, then you can take V in W to be, well, and let's say the coordinates are xi plus iyi, or xj plus iyj, and you take the v's and the w's to be taken out of d by dxj's and d by dyks and so on. You play with that, you'll find Nj is 0. So the easy thing is that if these coordinates exist, then Nj is 0. The hard thing is that if Nj equals 0, you have to prove the existence of holomorphic functions, of holomorphic coordinates. And so that's a PDE problem. You have to prove the existence of solutions to this, the holomorphic PDE, that prove the existence of solutions of the Cauchy-Riemann equation locally, provided that holds. Okay, so then.
What about you get holomorphic transition functions between these coordinates from the vanishing of this?
Yes, so that will be it will be automatic that if we take two different coordinate systems which are holomorphic in that sense, then the transition between functions between them is holomorphic. Okay. Okay. Well, so we call the almost complex structure J integrable. And then, well, it's an integral almost complex structure, and we just call it a complex structure. If Neuenhaus tensor Nj is 0, and then, well, by the and we call, in this case, the pair x comma j a complex manifold. Okay, so that gives us a second definition of a complex manifold. It's a real smooth manifold together with an integrable almost complex structure. Okay, and the claim is that these two definitions of complex manifold are equivalent. So, well, by the Newlander-Nirenberg theorem, this is equivalent to the first definition, kind of complex analytic definition of complex manifold. There exist holomorphic coordinate charts ui phi I covering x. So by holomorphic, I mean holomorphic with respect to j. And then it turns out that these form a holomorphic atlas curly A, which is the set of all phi i's, ui phi I for little I in big I, which can basically be the set of anything. Well, this is really phi I. I'm sorry. That's a different U. With my definition of atlas, the UI would be the image in here, and the phi I would be the inverse map to that. But anyway, you can make a holomorphic atlas. And conversely, so from A, we can reconstruct J. Okay, so there's two equivalent definitions of complex manifold. So, well, if we let J be an almost complex structure, on X, and nabla be a torsion-free connection on Tx. So then, well, nabla A of J BC. So you take the derivative of the tensor J with the connection, noting we can extend connections from tangent bundle to all tensor bundles. This and N ABC, they are tensors of the same type. They've got two T star X indices, one TX index. And, well, one can show that, or maybe up to a constant factor, Nj is a component of nabla J. So that is, we can use the almost complex structure to decompose the vector bundle containing this into various subbundles, and Nj is the component of it living in one of those subbundles. So therefore, so that if nabla of J equals 0, then Nj equals 0, and J is integrable. Okay, so that's going to be important when we get round to talking about the connection between complex structures and holonomy groups. If we've got a holonomy group H which preserves a complex structure just on R to the n, then by the connection between holonomy groups and constant tensors, there will be a tensor, an almost complex structure J on the entire manifold, which is constant under the Levi-Chivita connection of your metric, which is torsion-free, and therefore Nj is 0, and therefore J is a complex structure rather than just an almost complex structure. No. Well, the vanishing of nabla J is a compatibility condition, if you like, but no. And I'm saying J is an arbitrary almost complex structure, nabla is an arbitrary torsion-free connection. Then this is true.
I thought you would think like the J gives you a reduction structure, and then you would want that to be compatible with the connection.
Yeah. Well, you might like to. Well, if nabla J equals 0, then well, if that was true, then nabla is compatible with J in the sense that it also gives you a connection on the GLMC principal bundle, which lives in the frame bundle. But we don't need that. We only need a particular component of nabla J to vanish for this to hold. Okay, what else? Yeah, so another thing, so well, there is a natural notion of a holomorphic map between complex manifolds. So if you take the complex analytic definition, then you end up saying, well, you map from a chart in X, into Y, back into a chart on Y, and then the composition map has to be a holomorphic map between subsets of C to the M1 and C to the M2. For the so you just use kind of standard manifolds, way of defining smooth map for manifolds, but now with holomorphic maps. So in the brackets, almost complex structure definition. A map F going from X with complex or almost complex structure J into Y with the complex or almost complex structure K is holomorphic. If, well, F going from X into Y is smooth. Well, we can draw a diagram of vector bundles in X. Tx, the derivative of f df maps you to the pullback f upper star of ty. Tx can also map down by j to tx itself, and again we can map by df into f upper star of ty. On ty we have the complex structure k, so we can map down by f upper star of k. So the columns square to -1, they're isomorphisms. Well, basically this square commutes. In vector bundles on X. So this is essentially a Cauchy-Riemann equation. It says that the map df is complex linear, where the complex structures on Tx, the root multiplication j is acting by the root multiplication by -1 is j here, and the complex structure on Ty comes from k. Okay, so then complex manifolds and holomorphic maps form a category. So composition of holomorphic maps is holomorphic and so on. Okay, so examples of complex manifolds. Okay, well, some obvious ones. Easiest one would be C to the M. Important examples are the complex projective spaces, Cp to the M. You can make complex tori, T to the 2M, which can be, well, for example, C to the M divided by some lattice, which we could take to be Z to the M plus I Z to the M. Now, in fact, you can so the lattice here is some additive subgroup isomorphic to Z to the 2M to get something compact, and you can deform this lattice. You don't have to take it of that form, and you'll get different complex manifolds in general for different lattices. So these are both compact complex manifolds. More generally, in complex algebraic geometry, one can find, well, huge numbers of, let's say, compact complex manifolds defined as complex submanifolds of some, let's say, large dimensional complex projective space CP big N. So in general, if you want to make complex 3 manifolds, you might want to embed them in some space CPN for n much larger than 3, defined by the vanishing of some finite collection of homogeneous, well, let's say finitely many homogeneous polynomials in the homogeneous coordinates z0, z1 up to z big N of the projective space, and compact complex manifolds of this form are called projective complex manifolds. So one use of algebraic geometry, complex algebraic geometry, in this subject is as a very fertile source of examples. Okay. So next we're going to move on to talk about exterior forms on complex manifolds. So we'll have section 3.2 about exterior forms on complex manifolds. Okay, so well, let's take X and J to be a complex manifold in the sense of the second definition. So X is a real manifold, J is an almost complex structure whose Neuenhaus tensor vanishes. So then it is helpful to consider complex K-forms on X. In other words, sections, let's write them as alpha plus I times beta of the complexified bundle of K-forms, lambda to K T star of X, tensored over the reals with the complex numbers. And this is for alpha and beta are real K-forms. Okay, so don't get confused by the kind of two kinds of complexness going on here. So this business of complexifying the K-forms on X, this works on any real manifold. Has nothing whatsoever to do with the almost complex structure. You can do it for an odd-dimensional manifold or whatever. Okay, for any real manifold, we can consider complex K-forms, which are just pairs of real K-forms with a alpha plus I beta there. So this is now a complex vector bundle over the real manifold X. There's a difference between complex vector bundle and holomorphic vector bundles. A complex vector bundle is just something that lives on a real manifold, but whose fibers are complex vector spaces rather than real vector spaces. So we're doing this because the complex numbers are algebraically closed. So you can take eigenvalues and eigenvectors of things. In particular, we can take eigenvalues and eigenvectors of J. Whereas on the real manifold, on the real vector bundle, you can't necessarily find eigenvalues and eigenvectors of things because R is not algebraically closed. Okay, well, so the complex structure big J acts on real one forms as J takes T star of X into T star of X with J squared is minus 1. So we just do this by contraction of alpha lower b goes to J lower b upper A alpha lower A, contraction with of tensor indices in the obvious way. Now on complex one forms, T star of X tensored over the reals of the complex numbers. This is now a complex vector bundle. This has eigenvalues plus or minus I, because J squared is minus 1. And it splits as T star X tensored over the reals with C is a direct sum of two subbundles, one of which is the I eigenspace and the other of which is a minus I eigenspace, and the convention is to write them as T star of X with a 1 0, direct sum T star of X with a 0, 1, for reasons we'll see in a moment, where this is the I eigenspace, the eigenspace with eigenvalue I, and this is the minus I eigenspace. Okay. So that's what happens on one forms. Let's now see what happens on K forms. K is more than 1. So then, well, lambda to the K T star of X tensored over the reals with C. These are real K forms complexified. So here, this exterior power here is a real exterior power of a real vector space. And perhaps we could bracket it like that. So initially we take real K forms and complexify them. This is equivalent or isomorphic to taking a complex kth exterior power of the complexified real tangent bundle. This is now a complex vector bundle, and here we're taking exterior powers over the field C rather than over the field R. This is now lambda k C of, well, we now know that this splits as a 1 0 plus a 0 1 forms. Okay, so this is now the complex exterior power of a direct sum of the two things, and an exterior power of a direct sum of two things splits as a direct sum over all P and Q greater than 0 with P plus Q is equal to K of lambda pc of t star 1, 0 of x tensored over the complex numbers with lambda q c of t star 0, 1 of x brackets. So I'm decomposing my complex vector bundle of complex k-forms on X into a direct sum of complex subbundles indexed by natural numbers p and q which add up to k. So we define this to be direct sum of p plus q equals k of lambda p comma q t star of x. So by which I just mean that I'm going to write lambda pq of t star of x for this complex vector bundle here. Okay. So here, sections of this bundle, lambda p comma q of t star of x, are called p comma q forms. Okay, so what I'm saying here is that on the complex manifold, you complexify the k-forms. It's then natural to break the k-forms up into pieces indexed by p and q, where p plus q equals k. So in fact, so you can actually do this in terms of eigenspaces. So you might think that j squared should be -1 everywhere, so the only eigenvalues should be allowed for j are I and minus I. But actually that's a Lie group thing. So if you think about j as living in a Lie group, then j squared is -1. Really you should, for this point of view, you should think about j as living in the Lie algebra of GL m comma r at GL to m comma r rather than the Lie group, and then you can get a Lie algebra action of the Lie algebra GL to m comma r on the k-forms here, or complexified k-forms, and then actually this thing is the eigenspace of j with eigenvalue I times p minus q. Okay, so in the case k equals 1, either you have 1, 0, in which case you get eigenvalue I, or 0, 1, in which case you get eigenvalue minus I. So these things, they are in fact eigenbundles with eigenvalue p minus q times I, but you have to do something slightly non-obvious to make j act on the bundles, and when you do so, j doesn't square to -1 on the k-forms, as you might have expected. Okay, well, as to what PQ forms look like, that's actually fairly easy. If Z1 up to Zm are local holomorphic coordinates on X with respect to J, then the D of Zi's are complex 1 forms, because they're dxi plus I dyi, whatever. They're not real 1 forms, they're complex 1 forms. Also they're complex conjugates. D of Zi bars are also complex 1 forms. So the DZIs are 1, 0 forms, the D bar Zi's are 0, 1 forms. And so I can see that dz j1 wedge dot 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 wedge dz jp wedge dz bar k1 wedge dot 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 wedge dz bar kq. These are PQ forms, and they are in fact a basis of sections in fact, local bases of sections of lambda p comma q t star of x, and this is taken for the j's and the k's run over everything they could. So 1 less than or equal to j1 less than dot 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 less than jp less than or equal to m, and 1 less than or equal to k1 less than dot 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 less than kq less than or equal to m again. So locally any p comma q form can be written as a sum of complex functions times those kind of standard basis pq forms. Any questions so far? Okay, so far all this decomposition of k-forms is good for an almost complex manifold. You don't actually need the almost complex structure J to be integrable. The next thing I say does need that. So it turns out that D of, well, P comma Q forms is contained in P plus 1 comma Q forms direct sum P comma Q plus 1 forms. Well, at least for integrable J. So there's another interpretation of the, if you've got a general almost complex structure J, there's another interpretation of the Neuenhaus tensor Nj, which is that a D of a P comma Q form, it can also have components in P plus 2 Q minus 1 forms, and in P minus 1 Q plus 2 forms, and the Neuenhaus tensor is the thing which determines the maps from PQ forms into P plus 1 P plus 2 Q minus 1 and P minus 1 Q plus 2 forms. So if the Neuenhaus tensor is 0, then those maps are 0, and these live only in here. Okay, so we can write, it helps be a laser printer at this point. So straight D, the ordinary de Rham D, which is a kind of Roman D, is a partial D plus a partial D bar. So kind of curly D bar. So de Rham D splits as two pieces where curly D maps P comma Q forms to P plus 1 comma Q forms. So this is the kind of holomorphic part. It increases the complex linear, the holomorphic form, degree by 1. And D bar is a kind of anti-holomorphic bit. This maps P comma Q forms to P comma Q plus 1 forms. Okay, so we know that for de Rham forms we have, or for the de Rham differential, we have Roman D squared equals 0. If that tells you that curly D plus curly D bar squared is 0. And if you think about it, you'll see that we get curly D squared plus equals 0. Well, curly D bar squared equals curly D bar squared equals D bar plus D bar D is equal to 0. well, so initially d squared equals 0 tells you that the sum of these three terms are 0. Okay, but actually this thing maps you from PQ forms into P plus 2, Q forms. That thing maps you from PQ forms into P, Q plus 2 forms. This thing maps you into PQ forms into P plus 1, Q plus 1 forms. So each of these three pieces in the things which add up to 0 map you into different spaces. So you can deduce that each of these separately vanishes. So that's a useful thing. What you've got is a double complex, basically. So we're going to write big omega P, Q as the set of smooth sections of PQ forms. So that's a complex vector space, as this is a complex vector bundle. So that curly D maps omega P, Q into omega P plus 1, Q, and curly D bar maps omega P, Q into omega P, Q plus 1. Okay. So, well, a map, a smooth map, F going from X, or X, J, into C is a 0,0 form. Because 0 forms are just smooth functions. Therefore lies in big omega 0, 0. And if you work out what the definition means, it turns out that F is holomorphic if d bar of F equals 0. Okay, so well, d bar of F is kind of the anti-holomorphic part of the complex conjugate linear part of the derivative of F. So if d bar of F is 0, then the derivative of F is holomorphic, or is complex linear, so it's a holomorphic function. So that means we kind of prefer the operator d bar to the operator d, because d bar vanishing tends to give us holomorphic things, which we like, rather than anti-holomorphic functions, for example. So that's why if you're going to use one of d or d bar, you usually use d bar. When are we supposed to stop? Supposed to stop now. Let's just define Dolbeault cohomology groups first. So the Dolbeault cohomology groups are H, P, Q, lower d bar of X, which is the kernel of the d bar operator going from P, Q forms on X into P, Q plus 1 forms on X, divided by the image of d bar going from PQ minus 1 forms on X into P, Q forms on X. So they make sense because d bar squared equals 0, so the image is contained in the kernel, and they generalize de Rham cohomology groups. So this is a finer invariant to de Rham groups, and so there is a relationship between de Rham groups and Dolbeault groups. In fact, there's some kind of a spectral sequence going from these guys to the the de Rham cohomology groups. But it will turn out that for compact Kähler manifolds, that spectral sequence degenerates. So basically, these are pieces of de Rham cohomology. But so the dimensions of the de Rham groups give you invariant Petty numbers depending upon one integer k. Dimensions of the Dolbeault groups give you invariance depending upon two integers p and q. So there's more information in these somehow. Okay, so.